So I finished the previous lecture with an exercise that I left to you to show that a slice of a category is a right adjoint in some sense, or some. So today I want to start with the following proposition. This observation for categories as definition for the Simplicial sets, and then after this proposition I will explain with more details how to think about the slices of Simplicial sets. So and the proposition has three parts. In the first part have a simple observation, so functors where you take a join with some Simplicial set. So let me maybe say that x that I consider is just some Simplicial set, and then you consider join. Say you can take a join on the left, or you can join with x on the right, and the join is not commutative. So technically speaking, these two functors are different, but of course the properties are more or less the same. So you consider such functors from the category of Simplicial sets, but not to the category of Simplicial sets, but to the category of Simplicial sets under X. Right? So if you the kind of explanation for this, why this is under X, well, because if you take, say, join where X is on the left with some other Simplicial set T, right? So you always have a canonical map from the X to the join. And using this canonical map, you can always consider such join as sub-Simplicial set under a Simplicial set X. So you consider diagrams like this, and of course for maps you can verify that everything also works fine. So such functors preserve colimits. And you can notice that this is under X is quite important here, because if you drop this and you consider this functor from Simplicial sets to Simplicial sets, this is not true. So this is the first part of the proposition. So the second part, which follows from the first part, well. Okay. So then I consider this functor, well, say this one, where the x and the join is on the left. So this functor admits the right adjoint, which is exactly the slice. Right adjoint. So notation will be the following. So sending a map, so f from, say, S, say from, what's important is just notation for the map f, so from y to the x to the slice category x under f. Right, so that's a functor, it has a right adjoint. Right adjoint supposed to is it correct? No, it's not. It's the other way around. So the right adjoint supposed to take something in this category, which is just a map like this. So f from x to y, since this is objects under x, and it sends to some new Simplicial set, and this is just notation of this Simplicial set. And of course, there's kind of part 3, which is just dualizing everything in part 2. So. The same sentence admits right adjoint, sending now this will be from the x to the y to the slice, but this will be a slice not under f but over f. So the proof is very simple if you know some category theory. So say for the first part, I just noticed that what's a joint. So we have a formula for a joint. Take a joint, say, of x and y, right? Consider the component n. So this will be xn. Take this joint union with the xn minus 1 product with y1. So disjoint union, So you just kind of move around this index. And the last one will be, well, say, yn. So, and you can also immediately notice that if you consider just individual term in this disjoint union of this coproduct, is that say xa as a functor, so product with xa as a functor, from the category of the sets to the category of sets, well, this clearly preserves colimits. Right? So then I consider a functor where I just take y and send this to individual component. So take a disjoint, take a join of x and y, consider component n, and as a functor, this is functor from simplicial sets to the, maybe let me write this. So this is from simplicial sets to the sets, but this is now under xn. Right, so this is the functor. And with these two observations, it immediately follows, well, since in simplicial sets I can check everything for colimits component-wise. Right, so, and in each component, so the canonical map here from xn to this component will be just this kind of tautological map to this component, and all the rest is just commuted with the colimits by the trivial reasons. This is completely trivial observation. So on every component, everything commutes with the colimits, so the functor itself commutes with the colimits. So that's essentially the proof. So this is for the first part. For the second part, so this is standard categorical argument. So we just apply. There is in category theory, there is a special adjoint functor theorem, usually called Saft. So here we need to dualize everything. This is dual to the Saft. And the assumptions, if you want to apply, so you have a functor, like in this situation, the functor is joined with x. From one category to another category, the special adjoint functor theorem guarantees the existence of a right adjoint if you have several conditions satisfied. So conditions are the following, which are clearly satisfied in this case. So simplicial sets, so this category is complete. This is one assumption for a functor, for a category, complete, co-well-powered. So there is a notion of a well-powered condition, which is you can see in the Saft. Well-powered just means that sub-objects of a given object form a set, which in general in the category is not true. But here the condition is co-well-powered, meaning that the quotients of an object form a set. Okay, so this is co-well-powered, and it has a set of generators. So set of generators. And it's just a set of the standard simplices. So, and the statement of the Kosaft theorem is that if you have a functor between two categories, the domain category is satisfying these three conditions, is complete, co-well-powered, has a generating set, and the functor preserves colimits, then the conclusion is that this admits a right adjoint. So this is how we can use category theory here. So for 3, this is exactly the same. Okay, so from this kind of general categorical observations, we at least know that there is a right adjoint, so there is a slice, but we want to understand a little bit with more details what the slice is and how to work with it. So first of all, let me just rewrite the adjunction in the following way. So we have a bijections, so in 2 bijections for these 2 versions, 2 and 3. So in one version we have maps V bar. These are the maps in the following triangles. So this is in the category, say, under S. So I have S. So that's the diagram. Let me maybe just write the bijection and explain how to think about this diagram. So there's one-to-one correspondence with the maps from K to the slice F under. So this is map V. Okay, so it looks like I changed notation a little bit, so now this is supposed to be S everywhere in this statement to kind of to relate to this notation. But the meaning of this set bijection is still clear. So the slice is the right adjoint, right? So if I look at the map from some simplicial set K to this right adjoint, this is supposed to be a map from the left adjoint to this is not X, this is K, sorry. This is K, to the K, right? So this is the corresponding map, and this is map in this category under S. Hmm? SF. Thank you. Yeah. So somehow I changed my notation. Okay. Yeah, so this is the from the right adjoint functor, and this is from the left adjoint functor. And the left adjoint functor, well, we have a map V bar, and so this map is the canonical map through the joint, and the map F is given. So this is one bijection, and there's of course the other bijection for the second version. So here, this will be U bar. Say this will be now T. The join is in the other order, so this map is U bar. This is, say, that's not correct. This can be K, right? So this is. I think this is X. And this is X. Sorry for the confusion. So this is yes. So from the adjunction, yeah, this is a map to the slice. The slice for the map F, and this map is to the X. And this is the same thing as the map. Yeah, from the join. I think now everything is correct. Yes. Okay, so and the second version is more or less the same. So the difference is that now here on the left hand side the join is in the other order. So here is still there is some map F, and then the difference on the right hand side is that the slice is now not under F but over F. Okay, so check me one more time. Does it make sense from the point of view of adjunction of two functors? I think it works. So, but anyway, this is not something new. This is something that is hidden in just in this definition of a right adjoint functor. So then, yeah. So then there is a terminology. So let me just say that in some sources this is quite annoying because the difference in this notation is just where you put this slash under or over, and you can easily make mistake here. So this is slice under, so slice under, and also another terminology in other sources. This is coslice. Coslice. But I prefer not to use this terminology with coslice because since slice under or over, it's usually you can see from the notation what you're talking about. So this is X, say slice over, and also slice. Just a remark about terminology. There's terminology with slice and coslice. I will try to avoid this because from this kind of coslice you cannot recover what you're talking about, but from this terminology under or over you can clearly see what's going on. And this whole thing, maybe statements 2 and 3 in the proposition are called slice join adjunction. Okay, so that's a terminological remark. And then you can also notice, for example, that, well, if you want to understand, say, simplicial set, say you want to understand simplicial set, which is a slice over F. And to do this, well, you can just consider home, say, in the category of simplicial sets, from some standard simplex to the slice. Say, like this one, right? If you understand kind of this set and also all the simplicial operators, you have a complete understanding of the slice. But you can also rewrite this, right? So this is, by our definition, is the same as the home in the category of the simplicial sets. Now this is under S, so S joined with the standard simplex X. So this is where I consider this, my map F is a map from the S to the X, like in this situation. Right, so, and you can kind of forget about this adjunction, and you just take this as a definition, right? So this, if you have a simplicial set X, you fix this map, and then you say that you construct a new simplicial set, and the n simplices are exactly this set, and there are also simplicial operators that are kind of induced by the simplicial operators acting on this delta n. That?
For the first one, shouldn't it be S F slash because you wrote that an arrow F from X to Y it goes to X F slash, so the codomain is should be written with the F and slash.
So the other slash? Well,
I mean that's on the right.
no, this agrees with this, which follows from this part 2, right? So here I consider X which stands on the left, but in that because I want to use X as variable here, I'm using S in this statement, and S is on the left.
So we wrote that F goes to X under F.
F is a map from S to X.
I mean on the second line.
So here?
No, on the first board.
Yes.
No, on the left board.
On here?
Yeah, on the second line. We wrote that F goes to X over F.
Yeah, but this is just the same join, but now the argument is the second one. No, but still there is a canonical map. When you compute this join, this will be something under X.
Right.
So it has to be from X to something. Okay. So that's a kind of explanation how we can define this without the right adjunction. What else I want to say more about this? Okay, maybe I'll just prove next proposition. So on the next proposition, I assume that I have a sequencer map of simplicial sets and maps. So any sequence of maps. So this is of course in the category of simplicial sets. So T is mapped with the map J to the simplicial set S. This is mapped to the simplicial set X. Map is called P, and then there is map F to the simplicial set Y. So any sequence of maps of simplicial sets gives the following commutative diagrams with just two commutative squares. So I claim that there is a map from, well, there are the two versions because there are kind of two slices, over and under. So first version is for the slice under. So you take a slice under P, there is a map to the slice under the composition of the F and P. There is a map to the slice under the composition of the P and J, and there is a map to the slice under the composition of the F, P and J. and there's also the last map, and this square is commutative, so I'm going to call this square 1, and there is the same square where you just put the slice kind of before everything, so this is slice then p, so this is over slice simplicial set over p, then this is mapped to the slice over composition of f and p, there is another map to the slice over composition of the p and j, and finally slice over the composition of all the three maps. Let's call this square 2. So of course the proofs are more or less the same, so I'm going to prove only one. Okay. So essentially, if I want to prove, so this is we do 1, case 2, it's similar. So essentially, all the question is how we can define a map. So these two maps. Right, so where you have a slice, and then I can pre-compose the slice or post-compose the slice. If you can define these two maps, well, then these two maps are automatically defined, right? Because what's this map is just a post-composition with the J, and what's this map is just a pre-composition with the F. So it's enough only to understand these two maps. And these maps are kind of canonical. Well, since we have this adjunction and defined everything in terms of the adjunctions, I can use this adjunction to define these maps. So the map from the slice under P to the slice under the composition of the P and J, right? So is adjoint to the following, right? So by the adjunction kind of have you need to write something like a triangle. So the triangle will be like this. So this map is of course Pj, and this left map on the top is always a canonical map to the join. So I only need to specify this map, and this map I can specify as the following composition. So I can take join T and the slice over P. So then there is a map which is a join of the map J with the identity on the X of the slice. So this will be to the S join with this thing, right? So this is ID on the second component, and on the first component this is J, right? So this is T from T to S, and then I just take the counit of the adjunction, and this gives me the map, the missing map in this triangle, and the map of these slices is exactly by definition the adjoint of this map. And the second map, so the second map that we need to define from the slice under P to the slice of Y under composition of the F and P, again is adjoint. Now we have S. S is mapped to the S join with slice of X under P. Y, so this is FP, this is canonical, and the last one is again defined using the counit of the adjunction. So we have S join with the slice, take the counit to the X, and then take map F to the Y. So these are the definitions of these maps. So in terms of the adjunction, after I finish the proof, I'm going to kind of return to this naive description and also describe these maps in terms of the naive description and simplices. But I want a formal proof, and for formal proof I want to use adjunction. So this is what I do. So this, as I explained, this gives me these two maps. Automatically I can produce these two maps because this is just another thing when you take a pre-composition or post-composition. Well, and finally, This is a very simple but quite formal proof. Finally, why the square is commutative, so 1 is commutative. No, because well, you can kind of take this composition, you can take this composition, so because both compositions are adjoint to the same map. And the map is just the composition, so you take T, take a join with the slice of X under P, and then the map is join of J in the identity, so this is S join X slice of P of X under P, the counit of the adjunction, and F. So if you just now take these two definitions, apply them 4 times, and look at the composition, you'll see the same composition of this kind. And that's the end of the proof. Now let's look at several remarks.
So these squares are neither Pullbacks or push-ups?
No, this is just commutative squares. So, remarks. So, first remark is that, of course, we can look at a very special case where, kind of, in this sequence of 4 simplicial sets and 3 maps, I have actually only 1 map. So I start with the initial object, then there is kind of the canonical map to the S, then there is some meaningful map, let's call this P as before, to the X, and then there is another canonical map to the terminal object. Right? So kind of let's take a special case where J and F are as trivial as possible. Right, so then we can notice, oh, by the way, let's look, for example, at this map from the slice under P to the slice under the composition. So can you tell me what's the slice under the composition of the P and J in this case? Right, so this is definitely something kind of canonical, because this is just a map. We're trying to compute the slice for the map, which is just a canonical map from the initial object to the X. So what is this? Oh, you still have this definition here, right? Yeah, so in S here will be an empty set, right? You take a join with an empty set, and this is just delta n. So this condition under S, under empty set, this is automatically satisfied. So really, this will be just home in the simplicial set from delta n to the X. So this is the same thing as the X. So the observation is that whenever you have a map, you always have a canonical map from the slice to the X itself, as a special case of the map that we defined here. And of course there is kind of dual version that goes without saying, that you can just write slice in another position and you still get the map to the X. Now, second remark is that you can actually understand this map in terms of the simplices. It's not just something that's given by adjunction, but map, so the map, say, I think I'm working with the second version, what it's doing, so since, so I take a simplex, let's call this little x, so that's an n simplex in the slice. Right, so I take an n simplex in the slice, and it sends this. Now, first of all, we know that this under the adjunction, so corresponding, so the n simplex in the slice under adjunction, this is corresponding to the x with the bar from the delta n join S, which is mapped to the X. So n simplex, well, this is just this is still the same formula, but kind of you see that I use the join over P, right? And hence I change the order in the join. So take a simplex, look at the corresponding map like this, and so this sends this X to the following composition. So I take, well, it has to be another n simplex in the X, right? So this is the following composition. Delta n is canonically mapped to the delta n join with an empty set. So then the next map is the delta n join with the S, where empty set is mapped to the S in the canonical way. And finally there is this X with the bar, which is a map to the X. So you can define these maps using the adjunction, and I think this is a little bit easier and cleaner, but you can always think about this in terms of the simplices. So for example, this map on simplices works like this. Take a simplex and send this, interpret this as this X bar, this map, and send this to this composition, which is an n simplex in the target X. And finally, you can generalize everything. I'll try maybe to squeeze it here. So if you look more generally, so for example, what is the map from the slice of over P to the slice of Y over the composition of F and P, right? It sends, again, I take an n simplex little x in the slice, right? So this, I'm not writing words now, but this corresponds to the map X bar from the join of the delta n and S to the X, and it sends to the following composition, which is generalization. You take, yeah, you can map as before. Yep. In this case, since we have this adjunction, I need to write a map like this from the join. So in other order, so this will be the delta n join with S. This is mapped using X with the bar to the X, and finally there is map F, which is a map from X to Y. So this is a description. What is this map that we defined by adjunction is actually doing on the simplices, right? So I started with an n simplex in the domain, and in the target, the n simplex is supposed to be a map like this. Okay. So this covers the basics of the joins and slices for the categories and simplicial sets. And I want to go to the next section, which is joins and slices. So 4.3, I think. Joins and slices in lifting problems. So for me, this is one of the annoying sections of this course, because it's kind of very simple. There are no any substantial proofs. All the proofs are more or less tautological, but the notation and terminology is quite heavy. So it will be easy from a point of view of proofs, but still not easy to follow. So definition. So given maps of simplicial sets I, this is from A to B, A and B are two simplicial sets, and J from K to L, so maps of simplicial sets. The push-out join also called box join. You'll see why when I introduce notation for this. So I introduce this right now. So the notation is to take I and J, you write the join in the box. So this is defined as follows. Well, you have a diagram, take a join of A and K. There is a map from the B joined with K, and there is also a map to the A joined with L, right? So this is I joined with the identity on the B, right? So the second map is the identity on the A and the join with the map J, right? So then we can form a push out. So A join with L, push out with B join with K, and this is everything augmented under A join with K, right? And then there is B join with L, and there are two maps like this. So this one is just the identity on the B join with J, and this is I join with the identity in L. So this unique map that is induced from the push out to the join of B and L, this is called exactly the box join or push out join. Right? We've seen something like this when we, instead of the join, we use just the standard product. And this was in the beginning of the course. Now here we can upgrade everything and replace the one operation with another operation. But of course you can notice, and this will be quite important later, that this is non-symmetric. So warning, if you take a join, box join of I and J, this is not isomorphic to the box join of J and I. This will play its role later. Yeah, so this is analogous to the push-out product, and of course there is another operation which is analogous to the pull-back home. So that will be the next definition. So given a sequence of maps, like in the previous proposition, of simplicial sets, so T, S, X, and Y, with the maps J, P, and F. So the pullback slices are defined in the following way. So these are canonical maps, and now I'll try maybe to write a little bit bigger. So here you take the map F, you write this symbol, which is kind of this join in the box, in the power, and then this power has an index, which is the map P, and then after the symbol you write J, also in the power. So that's a notation for one of the pullback slices, and this is by definition a map from the slice under P and X to the product of the this is Y, FP, Y, FP, J, right? So you get this map when you prove the statement where you have two commutative squares for such sequence, right? From that square you immediately get this map, right? Because in this square you can kind of fix the vertices that here, here, and here. There's this vertex, so there's canonical map from this vertex to this fibered product. So that's kind. I don't want to draw this square again, but this is coming from that square. And of course, there is kind of another version for this. This for the slice under P. So the notation again with a little bit larger font. So this is F, and then you write to the power. First you write J, then you write this box join symbol with the index P, and this will be well essentially the same, but the slash is in the other position. Okay, So as you can see, this is already kind of a little bit annoying with this weird notation and terminology, pullback slices, and we need to prove some theorems about this. Okay, before I continue, maybe you have some questions?
So this join is not symmetric. Join is not symmetric.
No, join is not symmetric. Well, because it's kind of induced by the disjoint order disjoint union, and that's not symmetric. Yeah. And we can also see this in the following proposition. So proposition, it says the following. So again, given maps of simplicial sets, so map I from simplicial set A to B, map J from simplicial set K to the simplicial set L, and also map H from a simplicial set X to the simplicial set Y. So then the following are equivalent. Right, so the first condition is that you have a lifting property. You take a box join of I and J, and this has a left lifting property for the map H. Right, so this is the first condition. So the second condition is that you can take this J and move it from the left to the right. So I has a left lifting property with respect to the map, which is the H to the box join with index G, J. And that is true for any additional map J from the L to the X. And condition 3, since this situation is not symmetric, in this adjunction equivalences we have 3 conditions now. I can also leave J here. Consider J has left lifting property for the map H to the I box join with the index F, and this is for any map F which is a map from B to the X. So these 3 lifting problems are equivalent. But really we don't need to prove this because the method of the proof is exactly the same. Maybe I just draw for the situation. So first 1 and 2 is more or less the same as 1 and 3. So in the proof, say 1 is equivalent to 2. I just want to draw a diagram because this diagram will be useful later. So one lifting property is the following. So A with some map U is mapped to the slice over J. So here there is this complicated fibered product of slices. So this is the pullback slice H to the box join with the index G and then J. So here I have B and this map is I. So this is one of the lifting problems, and this is equivalent to the following lifting problem. So here I start with the co-fibered product of the joins over join. So this is mapped to the X, this is induced. Yeah, so this map I also use the same notation as before with V and W. This is U bar and V bar. Here we have box join of I and J to the join of B and L. This is map H, and this is W with the bar. And also this is a lifting problem. So the method of the proof is of course the same, right? So you kind of just look what data you have, and you have an adjunction, right? If you have a map like this, which you call U, then by the adjunction, this is a map to this slice. By the adjunction, you get a map from the join to the X, and this is map U bar that we discussed before. So kind of the method is exactly the same as before. I don't really need to prove this, but I just wanted to kind of fix notation and show you how this looks in the diagrams, because these diagrams I will need later in the proof of the Giles lifting and extension theorems. Okay. So next, the combinatorial lemma that I'm leaving as an exercise. So we have in the standard simplex n plus k plus 1, which I can also think of the join of the delta n and the delta k. So we have equalities of the following simplicial subsets. So first, well, you take the horn lambda and j, which sits inside the delta n. Take the box join with the boundary of the standard simplex delta k. Include this to the delta k, and this will be the same map as the inclusion of the horn n plus k plus 1 j inside the delta n plus k plus 1. So combinatorial exercise to verify that this is the same. So this is in the third assignment. By the way, the third assignment is the last one. Okay, then there is a variation where we kind of change the order with essentially the same proof. Yeah, and this works for any horn, not necessarily in a horn. You can take the left horns and right horns also. Okay, and the last one. So where you just take the inclusion of the two boundaries of the standard simplices. Okay. So the proof is exercise. Well, the combinatorics is not very hard. We've done harder combinatorics in the lectures. Okay. So from this, this is one lemma, and there is let's call this lemma 1, and let's call the next lemma 2, which is again has more or less the same proof as before when we do this, not for the box join but for the usual product. So let take S and T be classes of maps in the category of simplicial sets. So then, if you take weak saturation of X, take a box join of the weak saturation of T. This is contained in the weak saturation of the box join S and T. The proof is the same as for the product again, so no need to prove this. So finally, we can combine these two lemmas together . And notice that we have the following proposition. There's 5 parts. So first part, well, we take cell bar, which is the same as the monomorphisms. We take a box join with the monomorphisms, and this is again contained in the monomorphisms. right? Well, why this is so? Well, maybe I just explain the proof of the part one, right? So you can immediately see this if you just apply, if you take the combination. So cells are generated by such inclusions, right? So, and if you have this property, number 3, and you know this property, so it immediately follows that you have 1. And the other 4 statements are exactly of the same nature and more or less with the same proofs. You need to kind of find the one of the 3 parts in the lemma 1 and combine this with the lemma 2. So I'm just going to give you statements. You take the right anodyne maps, which is the saturation of the right horns, box product with the monomorphisms, and this is again contained in the inner anodyne maps. And part 3, monomorphisms on the left, box product, and left anodyne maps on the right. So this is contained again in the inner anodyne maps. So part 4.
Why is it in 2 and 3 is right horn and left horn and not just horn?
Because this is what we can show.
Yeah, but isn't it in this lemma we said that J could be anything?
Yeah, but you. Yeah. Yeah, but you also have something like this shift by 1 here.
Okay, but in the first you don't have something like that.
Well, you want to improve the statement too?
I want to see why it's right horn and not just. Since in the lemma, in the first we have all horns, yes?
In the first? Well, in the first, this is
The lemma on the right.
yeah. So yeah, let's look. So for example, we use condition 1, right? So you can take any horn and
Yeah, and you can take something like notes.
so just a second, maybe. No, just a sec. Yeah. Right horn. Oh, but this works. Well, this is still a correct statement, right? You can just kind of improve this a little bit and take any horn, right?
Yeah, I don't understand why we can't take any horn.
Oh, we can. Well, we definitely can take any horn, right? So then, if you take any horn, then you would
get
have
not inner horn, you get right horn, left horns.
yes,
Okay.
right or left?
Left, I suppose. If
Left horns,
J
right?
is 0.
Yeah, for j equal to 0, this is fine, but you won't reach this boundary, right? Because the j is bounded by n. Yeah, so you can improve this, but kind of in the applications, what I'm going to do next, this inner horns will be more interesting. Yeah, so in the statement 4, well, actually, I think this is what you want. So I can take the left horns, well, take a box join with this cell, and this is again contained in the left horns, right? This is what we discussed, right? So, and the same is true for the right horns. This is condition 5. So we take the cell with the bar, box join, right horns, and this is the right horns. Okay, so the proof is the combination of the lemma 1 and 2. Okay, so finally, next proposition. As I promised, kind of the hard part is the notation and maybe terminology, but the proofs are trivial. So again, in the next proposition, I assume that we're given 4 simplicial sets and 3 maps as before. So J, P, and I think this is now F and this is P. Okay. So then, with this situation, I want to introduce shorter notation. So I want to say that the map L is the pullback slice, which is P to the I box join with the index F, and R is P to the box join F I. Just to shorten the notation. Okay, so then we have the following. So part one, so I assume that I is a monomorphism, so closure of the cell, and I assume that P is a trivial fibration. So then, from this I can conclude that the L and R are trivial fibrations. Okay, so in part two, again I assume that I is some monomorphism, and P is now in a fibration, and this implies that L is the left fibration and R is the right fibration. So statement 3. I is right anodyne and P is in a fibration. So then this implies that L is a trivial fibration. 4. I is left horn closure, so left anodyne. So P is, as before, in a fibration, and the conclusion is that the R is a trivial fibration, and there are kind of 5 and 6 which are also dual as 3 and 4. So in the 5 I assume that I is a monomorphism and P is the left fibration, so this implies that the R is a left fibration. And finally, 6, I is a monomorphism, P is a right fibration. This implies that L is a right fibration.
Sorry for interrupting. I believe
That's the end.
You previously used terminology like GPF. I mean, the P follows from G. I mean, it's Y should be F, right?
So are you saying that I switched the
Yeah.
notation for F and P?
Right.
Yes, I did. That's unfortunate.
Yeah, is from T to S what now? I or J?
J.
And then in L there is I.
Yeah. So let's say this is I. Yes. Well, but I want to say that all these statements are very easy actually. So I'm going to prove maybe one, and then leave all other 5 as an exercise. Right? For example, if you want to show that 1 is correct, right? So what we need, well, this is a trivial fibration, right? So what's the definition of trivial fibration? It has right lifting property with respect to the inclusions of the boundaries of the standard simplices to the simplices. So I need to, well, first of all, I need to use the adjunction. So for example, the adjunction is the following. So I take the cell with the bar, so monomorphisms, and for example, I don't know, let me start maybe with the L. So I have a condition like this, right? So this is the L has the right lifting property with respect to this. By the adjunction, remember that I can kind of take this L, maybe I just use this. I don't want to rewrite the formula, plug in this kind of formula for L into this adjunction and use the adjunction that I formulated before. So this is equivalent to the following. So you have I, so then there will be a box join with the cell, with the bar, and this has to have left lifting property for the map P, right? But now we have we have something like, for example, in the previous proposition, the first one. Yes, so let me see the assumption. So the P is a trivial fibration, right? So this condition is satisfied if I know that this is a monomorphism, right? So this is any monomorphism, and here in the first condition it is given to me that I is a monomorphism. So using property 1, I'll get that this is true. So this proves, for example, that under these two assumptions, L is a trivial fibration. Now, to prove that R is a trivial fibration, you do exactly the same, but you use kind of the third statement from the adjunction. Instead of writing it like this, you just rewrite this. Well, it will be a cell and then box join and then I. And again, you use, well, R is the same. So I suggest, if you kind of have problems understanding this, and it's kind of understandable when you see this for the first time, I suggest that you do this 2, 3, up to 5 as an exercises, and you'll see that all the proofs that you have here is essentially just one line. You need to formulate the problem, kind of take the adjoint problem, use one of the statements of the previous proposition, and everything follows. But as an exercise, when you see this for the first time, I think this is a good exercise. Well, I've done this when I prepared this lecture to be sure that all the statements are correct. Okay. So let me kind of do the proof first and then formulate the statement. So if we assume that y is now a terminal object in this statement, map P is an inner fibration, which is equivalent. I want to use, since when I'm saying this inner fibration, I'm saying that X is an infinity category. So I want to use notation X, which is the same as C, is an infinity category. So, right. So then we get the following. So corollary. So given T mapped to the S with a map I, then there is map F to the infinity category C. So with C being an infinity category, so the pullback slices L and R. So the notation is the same as in the previous statement. So have the following. So first is that if I is a monomorphism, then L is a left fibration and R is a right fibration. So in particular, we can notice that we can take T to be empty set, right? So then there is only kind of one map, F. And then L, which is a map from the slice of C under F to the C. This is always the left fibration. And R, which is a map from the other slice, now this is over F to the C. this is always the right vibration. So condition 2, so statement 2, so I is right anodyne. This implies that L is a trivial vibration. And finally, I is left anodyne, implies that R is trivial vibration. So then I don't really need to prove this, right? Because the assumption is that the map P is an inner vibration. So I just need to find where I have these assumptions that P is inner vibration. This is conditions 2, 3, and 4. And the conditions 2, 3, and 4 now are statements 1, 2, and 3 here. So this is really just a special case. So I kind of developed this general stuff, and there is a very natural question. So I defined slices of simplicial sets. There was some other simplicial sets. Of course, the very natural property in this course would be that a slice of an infinity category is an infinity category. So finally, I can prove this as a corollary to this simple observation. So let now F be a map from S to C. So let be a map of simplicial sets. And I also assume that C is an infinity category. So then, slices under or over, doesn't matter, are infinity categories. Okay, now the proof is very, very simple. Essentially, maybe again I just say that everything is obvious, but let me just write one line. So first of all, clearly, left vibration or right vibration is an inner vibration. Is that clear? No, just to remember the definition of left and right vibration. This is the lifting property, and for the for the left vibration, you just have one additional lifting property. For right vibrations, you have also one additional lifting property. No, any left vibration is an inner vibration, clearly. Any right vibration is clearly an inner vibration. So I'm just want to show this statement as short as possible, hence the union. Right? But then, if I look at the following, well, for example, I look at one of the slices. For the other slice, it's exactly the same. So I have a map like this from the slice to the simplicial set, which happens to be an infinity category here. But so what's this with this slice? So this is R, right? Okay, and then there is kind of the canonical map to the point. So the observation is that this is a right vibration by the previous corollary, so this is inner vibration, and this is given to be an inner vibration since C is an infinity category. So this is a composition of two inner vibrations, which is again is inner vibration. Hence, this is an infinity category.
Excuse me, should we write slice over and slice up?
Yeah, this. Yeah, and so of course there is this another version of this. Here will be map L again to the C. This is map to the point, and this will be again an inner vibration. Okay, does it make sense? So this follows from this in particular part. Okay, so finally, as a sequence of these tautologies, which I kind of try to formulate all the statements that I know and all the statements that potentially could be useful, you get the simple observation that slices make infinity categories from infinity categories. Okay. And this finishes this section about the lifting problems. So I'm going to start the next section, in which I will prove the most important theorems in this chapter, but not today. Today I still need to do some preliminary work. So let's call this 4.4 Joyal's extension and lifting theorems. So the proof is based on this technique, on the lifting problems between these joins and slices, and also based on the notion of conservative functor and isofibration. So let me just say that for the conservative functors, the definition is more or less the same as the one category. So let C and D be two infinity categories. Let's assume that P is a functor, which just means that this is a map of simplicial sets. So is conservative if, well, we have the standard property, f in the C1 such that P of f is an isomorphism, implies that f itself is an isomorphism. So as usual, conservative functors just reflects the isomorphisms. Okay. So I have two simple remarks. First one is that the, say, functor f from C to D is conservative if and only if, just by looking at the definition, the functor induced on the homotopy categories is conservative in the usual sense for one categories.
So the pre-image of an isomorphism.
Well, it's not really a pre-image. You start with something. You start with a morphism. If you know that the image of this morphism is isomorphism, then this is an isomorphism. This is the reflecting property. And remark number 2, which is also trivial, if, say, f from C to D is conservative, then in particular you can you see that fiber is an infinity groupoid for any y which is a vertex in D. So fibers of conservative functors are groupoids, infinity groupoids. Okay. There are actually many examples of conservative functors, and this is important for the theory building of infinity categories. So, for example, left and right fibrations are conservative. So let me assume that I have a left fibration. For the right fibrations, it's the same proof, up to reversing several arrows. So let P from C to D be a left fibration. Okay, so let me fix F, some edge, and I consider this as a map from delta 1 to the C. So such that P of F is isomorphism. So I want to show that F is an isomorphism. Well, but then I have the following lifting problem. I take the horn lambda 2, 0, include this into the delta 2. On the right I have C, D, map P between them. So since this is a left fibration, I know that there is a solution for such lifting problem, any such lifting problem. So here the map from this horn, right? So the horn looks like, maybe I just draw it here. So it looks like this, right? So this is the face opposite the vertex 0 is missing. So I can take f and id here on this horn. So and define the map this to be by the maps f and id. Okay. So since I know that there's kind of the solution of this lifting property, well, it means that in the I can find something here, right? So maybe let me call this alpha. Right, so let's call this maybe sigma, and I formulate it as follows. So existence of the solution of the lifting problem sigma implies the existence of alpha such that have a composition I don't know. I don't understand my nose. It's quite complicated. So let me just maybe do this from my head. So I have this map alpha. So then what I will get from this is that I have alpha f, which is identity, right? So I constructed for the. I want to show that f is isomorphism. So alpha is the left inverse, right? But it's not necessarily right inverse. So what we can do then is take this lifting problem. So apply the same argument now to the map alpha. This is what I want to do, right? So why I can do this? Well, here to construct this lifting, to notice that the square is commutative, I was using that P of f is an isomorphism, right? So then, since I have this, I can apply P. I'll notice that the P of alpha, P of f is again kind of the identity. And I can apply this argument because the P of alpha is an isomorphism in D, right? So in the C, this is only left inverse, but when I apply P, this will be an isomorphism, right? Because I can take this to simplex, map it there, and this exactly tells me that there is an isomorphism. So kind of this alpha satisfies the same assumptions, so the lifting problem for alpha again makes sense and has a solution. So then I'll get that the alpha also has left inverse. But now this alpha has left inverse, and f is the right inverse for the alpha. Hence, alpha is invertible, hence f is invertible. And see that alpha has the left inverse. So thus alpha has left and right. So f inverse. By the associativity they coincide. So alpha is an isomorphism, and thus f is an isomorphism. That's the logic. And you can also notice that I didn't use that much from the left vibrations. I really just used this condition when n is equal to 2. So you can kind of formulate a little bit more general statement by noting that if such lifting problems has a solution, then the functor is conservative. Okay. So this is something that I want to say about the conservative functors between infinity categories. Okay. Now I have a question for you. Have you seen isofibration functors in category theory, in ordinary category theory, maybe in some other courses? This is why I kind of want to make a remark. So before I define an isofibrations and actually isofibrations in infinity category theory are quite important. So if I want, I can kind of do a chapter which is maybe chapter for 3 or 4 lectures just about either fibrations. So that's an important concept for the theory of infinity categories, but
Those are vibrations for some. Those are vibrations for some model.
yes, this is what I want to explain. So before I go to the isofibrations of infinity categories, just a kind of remark. So this whole thing is just a remark. Isofibrations of one categories. And this is not that important. So I don't know any textbook on category theory that has this notion. But this is important from the point of view of model category theory. So definition, so functor, so in this remark everything is just one category. So a functor P from C to D is an isofibration if I have the following interesting property. So for any object little c in the category C and isomorphism G from the P of the little c to some object D in the category D. So there is the lift. So there is C prime in the category C and isomorphism F from C to the C prime such that P of this isomorphism, little f, is exactly this isomorphism G. So in some sense this is saying that kind of if you have an isomorphism in the D and you can lift, in this case, the source, you can also lift this whole isomorphism. That's the definition. And you can see this a little bit in symmetric because I'm lifting the source, but you can also lift the target and the definition will be equivalent. Essentially, the equivalence is going from the G to the G inverse. Okay, so what I want to say about this is the following. Well, I can consider I the interval in the categories theory. So this is the category which can be uniquely, well, I can characterize this completely by saying this is a groupoid with 2 objects and 4 maps. So I'm not drawing the identity here and the identity here, but with these 2 maps there will be a total of 4 maps. So this, and I can consider this as an interval. So this kind of free standing isomorphism. That's the name for this groupoid. And a simple observation that functor is an isofibration. Well, since we love this lifting problems and right to left complements, or maybe just I say that isofibrations, maybe a proposition if you want, but I'm not going to prove this, proposition that isofibrations is exactly the left complement to the inclusion of 0, say this is 0 and this is 1, into this freestanding isomorphism. So this can be formulated in terms of the lifting properties. And another simple observation that kind of follows from this is that you can formulate that isofibrations are exactly the following class of maps. So you take a category, you take a map from the category product with the freestanding isomorphism. Well, this is kind of induced by this map, so let's call this little I, and this will be ID on the X and little I on the 0 to I. So X is any category, and you take the right lifting property. Right. So in other words, I'm saying that this class of maps is in the saturation of this class of maps. And this is not very hard to show, but if you look at this, you can notice that this is completely analogous to the Hurewicz fibrations. So iso fibrations are analogs of Hurewicz fibrations, but not in the topological spaces, now in the category of 4 small categories. And now I have a theorem about model structures. So theorem, which I find quite interesting. So there is a model structure on the category of small categories, well, such that the weak equivalences, I use my notation W, these are equivalences of categories, quite naturally. So cofibrations are defined in such a way that these are functors C from D, such that on the objects, this functor is injective. And finally, fibrations are isofibrations. So this isofibrations is a part, in some sense, natural model structure on the category of small categories. But more interestingly, so say this is part 1 of the theorem and part 2 of the theorem, there is exactly one model structure on categories, well, such that W are equivalences of categories. So there is this such model structure, and it is completely determined by what you take as a weak equivalences. Well, usually it's not the case. So, and in this sense, this model structure you call something like natural model structure or canonical model structure on the category of categories. Okay.
This is because I is an equivalence. I mean, this map from initial catchment to I is an equivalence.
This one?
Yeah.
Yeah, this is an equivalence of categories, yes, yes.
And I believe that from this, it's not hard to deduce this. The second statement.
Well, you still need to do something. Yeah.
I mean, that's the value of the second statement is that W turns everything. Right?
Yes,
and
yes.
It's really unusual.
Yes, for model categories, yes.
And I believe this is because.
Yeah, you're right, but this is kind of quite a degenerate example of a model category. For example, you can easily notice that every object is fibrant and cofibrant in this model structure. So there are really no resolutions, there is no homotopy category that's give you something new. So the case is degenerate, but the statement that there is only one such model structure, I think is still interesting. Okay, I think I'm out of time, maybe 5 minutes ago, so let me start.